So last time, as if you guys remember, we were talking a little bit about looking at the input equivalent noise generators, which usually are sort of useful from a spectral density standpoint. Because again, if I have some general purpose op amp and I'm not exactly sure how I'm going to hook the thing up, I want to be able to have sort of a fairly simple way to characterize its noise performance. So we said that obviously since many op amps have a non-infinite input impedance, we need to be able to model both the input equivalent voltage noise generator as well as the current noise generator. And we said that under that condition, because I might potentially have both, then obviously I need to be able to figure out what's sort of like the best impedance that I would want to use to actually drive this particular amplifier. Right? Because depending upon whether I'm mostly dominated by voltage noise or current noise, then if I change the source impedance, that's going to change the relative contribution of those two terms to the actual noise at the output. We said that also has some implications on, usually, unfortunately, of course, you don't actually get to control the source impedance. That's actually kind of fixed by what you're trying to do. So that would tell you that if I have a fixed source impedance, that implies what kind of amplifier would you want to use in order to basically get the best noise performance in that particular application. So obviously you can sort of take a look at what would be the total noise you'd get as a function of the source resistance. That's nothing too interesting other than it basically gets you to this formula or this sort of rule of thumb of if you know what the voltage and current noise generators are, then if you could actually pick the source impedance or perhaps do that by doing some impedance transformation, then basically the optimum source impedance you'd like to use is basically just the ratio of the voltage to the current noise. Okay? And again, this kind of intuitively makes sense because that's really what's going to be balancing out those two contributions. Now, so far when we've been talking about this, there's one thing that I kind of glibly, swept under the rug, and I mentioned we'd come back to it later. So maybe just, maybe somebody who's either seen this before or has an idea, so far in all of this analysis, what was I assuming about these noise generators that may actually not exactly be the case?
They're uncorrelated.
Yeah, that they're uncorrelated, right? That they have absolutely nothing to do with each other. Well, in reality, they could actually have a lot to do with each other, right? So just an example, if I had like a bipolar junction transistor or something like that, if I have some noise at the base, that's going to translate into noise at the collector. And so if you worked out sort of the equivalent noise generators, you'd actually have some correlation there. Okay, now, usually people ask sort of how exactly does that correlation happen? It's sort of a function of how the circuit is actually built. Okay, so it usually has to do with things that look sort of like, as an example, I might have, let's say, something like this, right, where I'm doing that input. So you can imagine noise that's sort of showing up at the output as voltage is also somehow related to noise that's showing up at the input as current. Okay? So don't worry too much about exactly what that correlation mechanism is because, depending upon the circuit, you can usually look at it and figure it out. But basically, we have to be a little bit careful because if there is actually any correlation, then all these calculations we did here, or really all these equations that I wrote right here, wouldn't exactly work because I couldn't just take, as an example, the Vn squared and add it to the contribution coming from In squared directly. Because if there's some correlation there, that kind of means that physically it's the same source of noise. And so now when you actually do the additions, rather than adding in the variances, you'd actually add in the standard deviations with whatever that correlated piece is. Okay? So I'm not going to walk through sort of the long list of math that creates. It's not too bad. It's just kind of annoying and not, at least in my opinion, hasn't been particularly useful in many of these sort of broadband circuits that we've been looking at. But just in case, you end up having to deal with something like this, there's a fairly simple way to include that correlation there. And the way you do that is basically like the following. So imagine that you had, this total noise current, and you just sort of decomposed it into two pieces. So one is going to be the uncorrelated component. In other words, this is whatever is really, truly independent of the voltage noise. And then there's going to be another piece that we're going to say is correlated with the voltage noise. And by correlated, I mean like fully correlated. That's kind of another way of saying that physically it came from the same source. Okay? So if I do that, then, and by the way, this is just kind of like vector decomposition, right? Where you have one thing that's totally orthogonal and the other one that's exactly parallel, right? So if I do that, then basically all that's really left for me to do is say, okay, so what is that correlated noise current as a function of the noise voltage? Okay? So in general, the relationship between those two would be some sort of impedance, right? Or since I've written this in the units of current over here, in this particular case, I would use admittance, okay? So what this YC here, that's just the correlation admittance. It just tells you how much of that input referred noise current, or how does the input referred noise current sort of get related to the noise voltage, okay? Now, I really am using admittance here because this could be a complex number at any given frequency, right? Because the correlation could be coming through like an inductor or a capacitor or something like that. And so that's why I've made that a complex number there, okay? But basically, once you've done this, you can go back, and again, if you're interested, you can sort of redo all of these equations here, just including the fact that some of the noise current is actually correlated with the noise voltage. And you can rederive what's the new optimum source impedance that would minimize the overall noise, okay? Again, it's not sort of particularly interesting, which is why I'm not going through the math here, but if you run into a situation where you really, have to be, where you really are, let's say you have a given amplifier you have to work with and you have to source match it, this is kind of the procedure that you would go through. Does this sort of make sense to everybody? Or? By the way, how many of you guys have taken 142? Okay, so you guys have all seen this before, right? Okay, so you should know very well how to deal with all that. Okay, so before we sort of move on to talk a little bit about just noise and feedback, there's a couple of loose ends, so to speak, that I wanted to tie up, okay? The first one has to do with, if you remember, we said that I was going to do this sort of sample and hold circuit, which originally I had drawn as something looking sort of like this, right? There was some, let's say, input voltage over there that we wanted to measure, and we just wanted to sample it onto that capacitor, right? So when we did that calculation, I kind of made a little bit of an assumption there. And the assumption was that I basically was going to close the switch forever before I actually open it to take that sample, right? Meaning that I've sort of let whatever is happening here, I'm trying to make that settle as much as I can, okay? But in practice, probably what you're actually going to do is, let's say you wanted to build an oscilloscope or an analog to digital converter or something like that. You don't usually want the sort of sample of the input at just one point in time. You actually want it sort of at many points in time, probably usually at a repetitive sort of time spacing, right? So as an example, if you bought a scope, it might be a 20 gigasample per second A to D converter in there, or even a 40 gigasample per second A to D converter, meaning it's taking samples every roughly 50 picoseconds or so, right? So the interesting question that comes up then is, well, okay, so if I'm going to be sampling this thing repetitively, and I want to look at the output of just what's coming from the noise component, obviously I have the signal inside of there, but if I want to know sort of how much of the noise is showing up, then now actually things get a little bit more interesting, okay? Because remember, I'm taking this white noise process over here, meaning the white noise from the resistor, which in continuous time is spread over all frequencies, right? I'm passing it through this sort of continuous time low-pass filter, right? So that's going to shape it to be, let's say, something like this. But then I'm sampling that thing, right? So what happens when I sample that thing from the standpoint of the kind of spectrum that I'm going to measure at the sampled output over here? What does that do? I heard somebody sort of say something about it. Anybody remember anything about sampling, or is this, back from nightmares in undergrad?
You get shifted versions of the spectrum?
Yeah, so whenever you sample something, right, what you're kind of doing is you sort of take pieces of that signal and you fold them back into the so-called Nyquist band, right? The Nyquist band is just basically the sample rate divided by 2, right? So every sample rate divided by 2, you sort of take that spectrum and fold it back over, right? Okay, so now actually you can get some sort of interesting effects. So let's sort of do 2 limits. So let's say that the bandwidth of this circuit over here is really, really wide. And in particular, the RC time constant there is really, really fast in comparison to my sample rate. Okay? So in that case, what do you think the sampled noise spectrum, which by the way is what I'm plotting over here, what should the sampled noise spectrum look like and why?
Aliased.
Okay, I agree it's aliased, but what does it actually look like in the sample domain? Does it look flat? Does it have a curve to it? Like, what does it look like? In other words, does it look white or does it look like something else again?
White.
Okay, I agree. It looks white. Other than that's what's being drawn on the slide or said on the slide. Why? Why does it look white again?
This is random.
Well, it's always random, so I'm not sure that really comes into the picture. So let's maybe actually find some space to sketch a little bit, and I'll do it over. Yeah, I've got a little bit of space here, so why don't I just sketch right here? Okay. So if I have that RC circuit, which again just looks like this, and I've got, of course, the noise over there, and then I'm just going to sample this thing. So I just said that if I had a really fast time constant, right, then basically I'm not going to be filtering that thing for a long period of time, right? As an example, let's say that my Nyquist, sample rate was sitting right here. Okay? So now, if that was the case, so fine, this first chunk over here, that's clearly white, right? Because I didn't do anything to that. Okay? How about this next chunk over here that I'm just going to take and stack on top of this? Still looks white, right? So notice, okay, fine, once I get over here, there's a little bit of curvature on there. But when I stack that, again, it's going to look pretty darn flat, right? And then by the time I get out over here, I've sort of filtered so much of that already that, maybe there's a little bit of curvature there, but the amount of noise I'm actually adding is pretty small. Because remember, this is sort of a log. If it's in dB, that means it's a log scale on the top over there, right? So that kind of means that if I have a really wide bandwidth in the continuous time, when I look at it in the sample domain, it should still basically look white. Because I'm just taking all these sort of chunks of white noise and folding them back on top of each other several times before I actually start filtering, right? Does this make sense to people, or? Okay, so now let's do a different case, and just to sort of somewhat make that clear, I'm going to have, let's say, a big resistor and a big capacitor, meaning I'm filtering it a lot more. Now, what's the sampled spectrum going to look like? What do you guys think?
Infinite spike right at the origin.
Oh, well, okay, if I made it like a zero, if I made it like zero frequency, then yeah. But, I don't want to push it quite that far. So let's say I have a situation like this. Okay, and just as an example, let's say my sample rate is like there. Okay, or maybe I'll even push it a little bit more just to make it really clear. Maybe I'll put my sample rate like over here. Okay? So now what is that sampled spectrum going to look like? Is it still going to look flat? No, right? Because I would take this chunk and everything to the left over there didn't change any, right? Then I would take this next chunk over here, and when I fold that back, that's kind of small, right? But basically it's going to maybe add just a little bit of curvature there. But since I've already filtered it before I even sampled, now I'm definitely going to have a low-pass shape over there, right? And obviously, the further I push the sample rate relative to this bandwidth, the more low-pass it's actually going to look, right? So that's basically what this plot right here is showing you. Okay, it's just saying, and by the way, T over tau, T is like the sample rate, tau is like the time constant of this filter. So you can see, as you make T over tau larger, meaning you make the tau of the filter faster, the sampled spectrum you get starts looking more and more white, meaning more and more flat, right? So if you took that out to infinity, it would just look completely flat like this. But if I made the T over tau 1, meaning the sort of time constant of that filter is the same as the sample rate, now you can see you have some pretty significant shape in the sampled spectrum. Okay? So why do I mention this? Well, what this basically tells you is if I'm going to be building a circuit that's going to have this sort of sampling in it, which, by the way, a lot of the circuits we're going to be talking about will do that, a lot of times we like to just assume that what we sample on this side is totally white, but that may not necessarily be the case. Okay? So it's only true if the sort of bandwidth of your circuit, or the bandwidth really of your sampler, is very, very fast, or at least fast enough in comparison to the sample rate. Okay? So for most of the stuff that we're going to be doing, we're actually going to sort of intentionally try and make it look that way. But as an example, if you built like a filter where you've intentionally put some low pass into there, that may not actually be the case, and so you may actually have to be careful to keep track of the fact that the sampled spectrum is not actually white. Okay? Now, by the way, just to be clear, does any of this change the total noise that I'm going to measure? Meaning, if I looked at the variance of the noise, would any of the stuff I talked about really change it, or no? Just for this simple RC circuit. In other words, as I change, let's say, this resistor over here to change the bandwidth relative to the sample rate, would that change the total amount of noise I measure from a variance standpoint? Who thinks it changes? Doesn't change? Okay, good. So why not?
It's only dependent on C.
Okay, I agree it's only dependent on C, but I've done all this weird sampling and aliasing and all this other junk. So why by the way, you're right, it doesn't change, but why doesn't that change anything?
Then if you integrate it over the spectrum, you're going to add the same amount because...
Yeah, exactly, right? So when I do that sampling process, I'm grabbing these chunks and folding them back, but the total amount that added is no different than it was when I integrated over the entire spectrum, right? So that's exactly what's happening there. Okay, so again, just the only thing you have to be careful of is if you use this thing in some other filtered context, where there's a filter in the sampled domain, then you have to be a little bit careful about it. Okay, but the total noise variance, that fortunately, at least at this point, does not actually change. Yeah?
Are the cases the same?
Case is the same. What do you mean?
The top circuit that you have drawn.
Top circuit. Oh.
This one, yeah. So what happens in that case?
They're basically the same. They're not exactly identical, but they're basically the same. So the only thing that's obviously a little bit different here versus there is that noise process over here is continuous, whereas over here I'm sort of stopping it and taking samples, okay, on the top circuit. So if you really had something where this top thing didn't fully settle, then what you'd actually end up with is a slightly different answer than this. Simply because from one sample to the next, you wouldn't have time to actually settle things out exactly. Okay? But ballpark, you'd actually get this similar, if it means it didn't settle, that kind of says, again, the spectrum got shaped to be a low pass kind of thing. You'd have a very similar shape. In detail, it's not exactly the same, but it's pretty close. It's a good question. Other questions? Okay, so now there's actually one last loose end that I need to just mention briefly. I'm not going to spend a lot of time on it, but you'll probably hear about it at some point, which is why I just want to mention it here. If I really did have something like the circuit that I was drawing before, and this is actually tying into Shiva's question. So let's say I really did do something like the following. So I have some resistance from the switch. I have a switch over here. And then I drive that onto a capacitor, okay? And let's say this switch right here, I'm going to turn it on and off periodically, okay? Now, if I'm really doing this, if afterwards I was only looking at like samples at, let's say, particular instances, meaning like I'm kind of doing something, ideally speaking, that looks like this, meaning that I only sample it again at like these Dirac impulses, meaning at one particular instant of time, then you'd see something that basically looks almost identical to this, okay? Or the other curve, depending on the bandwidth, obviously. However, let's say that's not what I'm doing. let's say what I'm actually doing is I'm going to look at this thing in continuous time. Okay? And I just want to know what is the spectrum of noise at this output over here. So now, what's a little bit weird about this? What would like the noise waveforms kind of look like here? What do you guys think? I just looked continuous time at that output right there. Just, if you were to kind of sketch or, have an idea of what that noise wave, and I guess I should be careful. When I say noise waveform, what I mean is something like, how would the variance change over time? Or maybe just as an example, if you just stuck this into a scope, what would that scope trace look like?
Ringing at the edges.
Okay, well, yes, that's like a second order thing I'm not even worried about. Let's assume it really is this circuit right here. So what would the trace kind of look like?
Maybe like the sync function.
Well, you're thinking in the frequency domain. I'm thinking something really simple. I'm just saying, I just literally take this output right here and I shove it into a scope, right? So let's see what that might look like. And again, just to give myself a little bit of space, well, okay. Can you guys see over here? Is that enough space? Shake your head if not. Okay, so let's say that was my scope, trace right there. What you'd see is something like the following. So when the switch is on, I'm going to have some noise, right? Then once I sample it, it's going to stop, right? It's just going to get stuck there. Then when I turn the switch back on again, I'm going to have some noise. And then it's going to get sampled. And then noise, sampled, right? Okay, what's sort of interesting about this particular waveform here? From the standpoint of looking at the noise characteristics versus time. What's a little bit different about this than if I didn't have that switch right there as an example? What do you guys think?
Periodic.
Yeah, there's some periodicity there, right? In particular, if I happen to sample this thing there, right, on a periodic basis, versus let me just do it with a different color. Let's say I was instead sampling it there, right? The characteristics I see are kind of different, right? Because here, no matter sort of where I sample it, I'm always going to get the same answer. Whereas in here, if I shift it ever so slightly, I see a slightly different behavior, right? So what I'm kind of getting at here is that in many systems, you can actually have exactly this kind of behavior where essentially the characteristics of the noise are changing periodically over time, okay? So this happens a lot when you have things like sampling networks. It also happens a lot in things like oscillators, where even the amount of noise that the device is injecting may actually change over the clock cycle, okay? So what I'm kind of getting at here is that if you really have something that has this sort of periodic behavior in the system, what you may actually need to look at is the periodic variation of the noise, or the periodic characteristics of the noise. And what that means is that, if I was to carve the sort of the period up into little time chunks, at each one of those time chunks, the behavior of the noise might actually be different. Okay, so you could do a plot of, let's say, something like time versus the sigma of the noise. And believe me, there are circuits where you'd see something that looked like that. Okay? So again, why do I mention this? Well, because actually many circuits that you deal with will have these kinds of characteristics. So particularly things like oscillators, or things like these sample and hold circuits. Or in fact, later we'll be talking about this quite a bit more, and you'll have lots of fun actually characterizing this. Things like comparators, where you trigger it with a clock, and then all of a sudden it makes a decision. Also have these very sort of sophisticated, basically time-varying noise characteristics. The good news is it's periodically time-varying, so you can still actually do some calculations with that. And maybe from a practical standpoint, the even better news is there's actually now new simulators, not really new anymore, but things like Spectre and not HSpice, unfortunately, but Spectre and some of the newer versions of Spice, that can actually do simulations that would tell you these periodic variations. Okay? So by the way, just in case any of you guys are sort of statistical signal processing geeks, this is called cyclostationary noise. Okay, stationary noise means that the characteristics don't change at all over time. Cyclostationary just means that it periodically changes. That's why it's cyclo in the front. Okay? So again, if you run into this, then, again, I'm not going to spend any more time on it here in class, but just you should know there is a way of actually dealing with that. And you probably will run into this at some point during your career. Okay? So, if you're interested, you can always come bug me later, but basically the sort of the type of analysis is known as periodic noise analysis, or P-noise analysis. Okay, it's usually associated with, you do a so-called periodic steady state first to figure out just, over a period, what is the circuit actually doing? And then once you know that, you can figure out the noise characteristics at each one of those sort of time points inside of the period. Okay? Does this sort of make sense to people? Or, by the way, anybody ever heard of this before, or this is completely new to people? Did he talk about this at all in 142? No. Okay. All right. Well, so, if you're curious as to why something like this is interesting, just go, type in Google oscillator phase noise, and you'll see, 100 years of literature about how it's all weird, and there's all these variations over time, and how you have to do these weird impulse sensitivity functions. Long story short, it's actually something that's practically of interest, so that's why I'm kind of mentioning it. But for now, most of the things we're going to deal with, we're going to just not worry too much about it. But definitely, if you run into something like this, you need to just know what is actually going on there. Okay? Any kind of questions on this? Or? Okay. So with that, let's actually go ahead and move on to the next set of lecture notes here. This is going to be sort of our final foray through noise explicitly, although we'll be seeing that noise is going to keep sort of popping back up as we talk about real circuits as well. So the last thing I want to talk a little bit about is just, obviously since this is an analog circuits class, we're going to be using a lot of feedback, right? Well, if we're using feedback, it's obviously an interesting question to ask. Well, if I'm going to put something into feedback, is that going to change my noise performance? Okay? So this is actually kind of an interesting discussion for the following reason. So if I was like a pure linear systems mathematician, then I would actually claim that basically taking some amplifier, let's say, and putting it into feedback should not have any impact on the input referred noise. Okay? Because if you kind of think about it, and let's just draw this. Again, let's say I have some ideal amplifier, and then there's some ideal feedback gain block like this, right? Basically, when I add that feedback in, anything that I do to the noise over here, I'm also going to be doing to the signal, right? So because of that, I would claim that this feedback should basically have no effect on the input referred noise, right? Because I'm just basically changing the gain of both the noise and the signal itself. So if I'm doing that, there should be no actual change in sort of the effective signal to noise ratio I get. Okay? Does this make sense to people, or? Okay, so now the bad news is, well, okay, I was going to say the bad news is you're circuit designers and you have to build real stuff, and real stuff never works that way. But by the way, that's kind of the good news because you get to actually build stuff. So, it's not that it's bad news that you're circuit designers, it's just you have to deal with more stuff. Okay? But again, that means that usually what ends up happening is when I actually build this feedback loop over here, or that feedback network, unfortunately the things I use to build that feedback network generally have noise in them. And since they have noise in them, that noise that they produce is going to actually degrade the overall noise performance, right? Because obviously anything that I add that has noise can't possibly make the life better, right? So what I'm going to spend a little bit of time talking about today is just the unfortunate sort of consequence of that and how we can relatively simply figure out the amount of extra noise we're going to get from that. And also we'll actually see that there's some, not exactly corner cases, but there's some interesting ways that even though you'd think that basically doing the, tying the amplifier in that particular configuration shouldn't change anything. It actually does end up modifying the noise performance. Okay, and the best way to see that is by example, so we'll go through that in 1 second. Okay, so let's just start out with what happens when I have to deal with real life, and I actually have some real feedback element, and that feedback element adds in some noise to my system. Okay, so conceptually, this is actually pretty easy to deal with. Right, so I could always just take my amplifier, which again, I'm going to pretend as a two-port, I'm going to model it as a two-port system. And let's say in this case, I added some feedback resistance to make this like a transimpedance amplifier. Okay. So conceptually, if I wanted to figure out how much extra noise this thing is adding, I can just go back and do the exact same calculations I had done before to figure out the input referred voltage noise and the input referred current noise, right? So if I wanted the input referred voltage, I short out the input, right? And that would tell me the input referred voltage noise, including this feedback resistance here. If I wanted to know the input referred current noise, I leave this as an open circuit, right? And when I leave that as an open circuit, I would get only the current contribution, okay? So conceptually, really easy to do, but again, the calculations get pretty tedious. Just because, especially if I gave you some more complicated feedback network or some weird input impedance on the amplifier, you can just get a bunch of, basically math to get the answer. So instead, what I claim is, from a practical standpoint, most of the time you can actually do something a little bit easier. And basically, the easier thing to do is essentially just figure out basically what the loading, quote unquote, of that feedback circuit is on the input, and then just take the noise associated with that loading and directly add it into the input. Okay? So to be more specific, let's just say, I take this shunt feedback over here, which again is just like the transimpedance amplifier configuration. So here, and by the way, again, I'm really interested in just what's the extra noise coming in from that RF over there. Okay, so anytime I have a noise calculation, I can do one of two things, right? I can either model the noise as being a current source in parallel with that RF, or a voltage source in series with that RF. So here, since I'm particularly interested in just coming up with kind of like a fairly simple way to figure out what the extra noise from this thing is, why is it that I chose to use a current right here versus a voltage? So in this particular case, why did I go with current? Any thoughts? Just as a reminder, if I have a shunt feedback circuit like this, what's the units of the input I should be using? In other words, what type of input should I be feeding it with?
Voltage.
For something like this,
Got it.
yeah, I want to feed it with current, right? Because I have a shunt feedback, I've created an input resistance now, right? So I'm trying to essentially take an input current and then translate that into a voltage, okay? So if the units of this is current at the input, it makes sense that if I'm interested in the noise impact, I should basically try and figure out how much noise current am I going to be adding from that feedback resistance, right? Well, so if that's the case, and again, assuming that I've kind of got a good feedback loop, meaning I added this shunt resistance because I had a pretty high input impedance to begin with, and I have a good output, a good amplifier with a low output impedance, then basically the quickest way for me to approximate this is just to say, okay, all of that noise current is basically just adding directly into the input, right? If I wanted to do this, then I would basically say, rather than having just the native noise current from the amplifier, I'd say that the effective noise current is the native noise current plus 4 kT delta F over RF, right? Which is just, again, this is just the noise current from that shunt resistor, okay? Not exactly correct, but actually in 90x% of the cases basically gives you the right answer. So now let's actually just look at another example. So let's say I do this so-called series shunt feedback network. Or, by the way, this would typically be something like, a non-inverting amplifier, right? So let's say I do something like this. So here, my input is a voltage, right? If I want to figure out how much noise this feedback network over here is adding, again, I'm interested in essentially voltage. Now here it's actually sort of even easier than it was before, because if you kind of think about it, any sort of noise voltage that shows up like this is exactly equivalent to noise voltage showing up like that, right? So again, if the output impedance of that amplifier is basically close to 0, or at least small compared to these resistors, then it's pretty easy to figure out how much voltage noise is actually coming through over here, right? Because effectively, if I have remember with noise calculations, you always ground the input. So that'd be kind of like saying that I have a grounded input into the amplifier, and then it's just feeding back through RE and RF, right? Well, hey, a grounded amplifier inside of there, that's just basically a 0-volt voltage source, right? That's going to be driving that RF right there. By the way, a 0-volt voltage source just looks like a short. So essentially, I've just got RE like this and RF like that, driving the negative input of the amplifier, right? So now life is pretty easy, because so I've got RE just in parallel with RF, like this. Then obviously the voltage noise is just 4 kT times whatever the parallel effective resistance is, which of course here is just RE in parallel with RF. Okay? So for something like this, just like before, I just take that effective voltage noise and add it to the real or the intrinsic voltage noise of my amplifier. Again, not that this is exactly correct, but 90x% of the time basically gives you close enough to the right answer that, if I really got something complicated, this is basically what I would do, just to kind of get the quick and dirty and pretty close to the right answer. So again, kind of name of the game here is really just figure out what the right units to use are, meaning either voltage or current. And that basically is going to be set by the type of amplifier you're building. And once you know that, you can quickly figure out how much extra noise should be added by this particular feedback network. Any questions on this before we move on? Or? Okay, well, so let's actually take a look at a couple of interesting examples just to make sure all of this is really clear to everybody. Okay? So let's say I'm going to actually take this non-inverting amplifier that we kind of talked about a second ago. So I want to build that thing up, and if I'm building that amplifier, these resistors over here, they're really just supposed to be setting my feedback gain, right? Other than that, they're not really serving any useful purpose for me, right? So if I wanted to do a low power design, I would try and make these feedback resistors pretty large. By the way, why do I say that? Why do I not want to make these really small resistors?
Bias current.
Yeah, it's just I'm basically spending current to drive those resistors statically, right? So I want to make those things large just to minimize the amount of current I have to spend to actually create that feedback loop, okay? So just as an example, let's say that I wanted a gain of 10. As I'm sure you guys all know, the gain is obviously just set by, the closed loop gain, of course, is just 1 plus R2 over R1, right? No, did I get that wrong? No, it's R1 over R2. There we go. Right? So basically, if I've done that, then very quickly I'm sort of stuck with, let's say I just arbitrarily pick that R2 is 100 kilo ohms, okay? Just because, again, I want a large resistance there. Then to get that certain gain, I have to make sure that R1 is now going to be 900 kilo ohms, okay? So now from a voltage noise standpoint, I'm just going to get 100 kilo ohms in parallel with 900 kilo ohms. And that's going to turn out to be about 40 nanovolts per square root hertz. Okay? Just in case you guys don't remember, that's a pretty big number. So if I looked at, let's say, the voltage noise I had from a 50 ohm resistor, that's something more like a nanovolt per square root hertz. Right? So this is really, really big in comparison. Right? Especially if the whole reason I was doing this was that I had a reasonably small input signal and I wanted to amplify the thing up. Okay? So that's kind of crappy, right? Because, again, this thing really isn't doing anything for me. But it might actually end up totally dominating my noise performance. By the way, just to maybe see, anybody have an idea of if you went and you bought like some good BJT op amp, what the input referred voltage noise might be? Or even a FET op amp, let's say? Anybody ever looked at those spec sheets? Oh, you guys took 142, so you must have looked at one of those at some point. Or you just tried like 5 different chips until it worked. Anybody ever looked at one of those spec sheets? Or? No, okay. Well, so maybe I should really give you a homework to go and look up one of those spec sheets. But just to give you an idea, again, a good op amp is probably sub nanovolt per root hertz input referred voltage noise. Okay, so if I was really to do something like this, it's kind of expensive. Right? It's kind of painful from a noise standpoint because, again, that stupid feedback network is just there to set the gain, but now it would totally screw up my noise. Okay, and the piece of bad news there is, of course, if I want to do better than this, my only option is essentially to spend more power, right? I basically just have to drop these resistors and then spend a bunch of power driving that bias current there, okay? At least with this particular configuration. Now, as we'll see a little bit later, there's actually better things we can do. In other words, maybe this configuration for using op amps and resistors isn't actually the right way to do the feedback. And we'll see that maybe in a couple of lectures or so. But this is already kind of giving you a hint that this is a little bit annoying here, right? Because just adding that darn feedback loop in is actually messing up my noise performance. So there's actually another sort of even more interesting example that we'll spend a little bit of time on now. So we did the non-inverting amplifier. So obviously, maybe we should look at the inverting amplifier too, just to sort of see what's going to happen there. Okay? So now I'm actually going to claim that life is even worse than it was before. Okay? Because now what I want to do just to prove a point, I'm going to even pretend that I can build these resistors as being perfectly noiseless. Okay? So I've actually given you the magical element that all the mathematicians like to have. Right, so I can ideally set the feedback gain without adding any noise from these feedback resistors. Well, what we're going to see in 1 second is that actually, even if I did this, I'm actually going to be amplifying the noise. And at this point, somebody should be like saying, what the hell are you talking about? You said in the beginning that if I gave you ideal feedback gain, then nothing should actually change. Well, we'll see what's going to happen. Okay? So let's just kind of walk through this really quickly. So from the standpoint of the input signal, right, again, I'm going to completely ignore any noise from R1 and R2, but I'm just going to have some noise from the op amp. From the standpoint of the input signal, the gain is just minus V1 times R2 over R1, right? Just your standard thing back from your very first circuits class. But now let's think about what the gain from the standpoint of the noise actually is. Right, so remember the input signal, that's sitting over here, but the noise, that's right at that input terminal of the op amp. Okay? So from the standpoint of the noise signal over here, it's maybe not immediately obvious, but the noise signal is kind of connected in the almost non-inverting configuration, right? Where the gain is actually 1 plus R2 over R1. Okay, and just in case you sort of don't believe me, the way to see that is something like the following. So everyone should agree that because it's noise, it doesn't matter which polarity I connect it to, right? So I can always say that the voltage is sort of reversed. right? Well, if I'm okay with doing that, then I can take this voltage noise over there and basically put it down at the bottom, right? Just tie it onto the other input of the op amp. So now if I do that, should be pretty clear. I just have that non-inverting configuration, right? Make sense to everybody here? Okay. So once I've done that, then again, you can pretty quickly show just the gain there is this 1 plus R2 over R1. Well, so now if you sort of pay close attention here, it should already be clear to you that something bad is about to happen, right? Because the gain from this noise right here is not the same as the gain from the input signal. And so you can do some manipulations. I'm not going to walk through them because they're not particularly difficult. If I manipulate these expressions, what you're going to end up with is something like the following. That the input equivalent noise voltage is actually whatever the noise voltage from the op amp was, times this 1 plus 1 over the gain squared. Okay? As an example, if I use the gain of 1, I would actually be quadrupling the noise variance. If I use the gain of, let's say, 2, it's not quite as bad. It's 1.5 squared, right? But clearly, this factor right here is greater than 1. Okay? So now, here's the question to you guys. I had no noise whatsoever from the resistors. So how in the heck is it that by tying the op amp up like this, I've actually increased its input equivalent noise? What happened there?
Like you said, you used the wrong topology.
Okay, well, I used the wrong topology, but, still, I have perfectly ideal resistors and everything here, right? So this is kind of weird, because I didn't add any noise from the resistors. So you're kind of right, by the way. It is actually the wrong topology, but specifically, what's wrong about this topology?
There's no cancellation resistor on the non-inverting or on the non-inverting input.
What do you mean cancellation resistor?
Can you make the two cancel?
Unfortunately, I don't think so, because if I added another resistor, even if it's sort of, non-ideal or whatever, or actually, especially if it's non-ideal, it's going to mess things up. But this is a slightly different input. So actually, you might be really clever and you might be able to do what you're saying, but let's actually get to the reason why that might work.
The node of input signal and the input referred noise is not the same.
Okay, you're right. They're actually not at the same node. Why is that a problem? Or to say it another way, what did we talk about this lecture and last lecture that would sort of explain exactly the issue here?
Have different gains.
Okay, they have different gains. What is that kind of related to? And I'll give you a little bit of a hint. What does that thing on the right over there look like?
Source resistor. RS.
Ah, there we go. Okay, so that thing on the right, that's the shunt feedback amplifier, right? That shunt feedback amplifier has some input-referred noise current, effectively, right? So now if I go and I add this other resistor in the front right here, what I'm basically doing is I'm changing the source impedance, right? Well, as soon as I change the source impedance, bingo, I'm going to get a different noise at the output, right? So actually, maybe what you're saying before really is correct. I really did use the wrong topology, in the sense that I created a topology that has, a certain input impedance, and then when I added this resistor over here, I basically messed up the optimum source impedance to drive it with, right? And by messing it up like that, that's what's responsible for that extra noise factor, okay? So just in case you were wondering, why we went through all that stuff about source impedance, this is a really good example. Because it's kind of innocuous, right? You'd think that, maybe I can make the resistors big enough that they're not that big of a deal, they're not going to cause any problem. Well, guess what? Doesn't actually matter what you had chosen there. Even if they were perfect resistors, you'd still actually mess up the noise performance, simply because you changed the source impedance. Does this make sense to everybody, or? Okay, so unless there's any sort of more questions on this, the last thing I wanted to do before we sort of move on officially from noise is just walk through one more example related to all of this, okay? And so here, as we're going to be talking about a little bit more, I'm actually going to claim that I'm going to come up with a better way of doing that feedback. And probably many of you will have heard this. Well, this will be happening all the time in, again, about a week or so. I'm actually going to be doing the feedback with capacitors, which if you ever build a switched capacitor circuit, which you will be doing in this class, but you may have heard in the past, that's actually sort of the way you'd actually do things. So to go through that example, let's just, take a look at it. So the amplifier I'm going to build is going to be a very simple common source amplifier. But now, again, instead of doing the feedback through resistors, so this is, again, the sort of inverting amplifier configuration, I'm actually going to do the feedback through capacitors. Okay? Let's have some load cap over there, some feedback capacitance, some source capacitance, and that's where my input is going to be coming from. Okay? And so to make my life easy, and by the way, because it basically gives you the right answer anyways, I'm just going to assume, I have this perfect current source load, and the transistor has infinite output impedance. Okay? So just to make sure it's clear, as I mentioned before, this really is the same amplifier as what we had just looked at. It's just that I'm doing the feedback through capacitors instead of resistors. Okay? And so here, because we're doing the feedback through capacitors rather than through resistors, the gain, rather than being R2 over R1, as it is over here, is actually going to be CS over CF. Just because, capacitors, the resistance is like 1 over the capacitance, right? Okay. So now what I want to do is go through and figure out what's the effective noise at the output from this amplifier right here. So you guys tell me, as usual, what's like the first step I take? What do I do?
Ground the
Yeah,
input.
ground the input and draw the small signal model. Okay, so let's go ahead and do that. I'm going to draw it in a particular way. You'll see why in a second. So I'm going to have a CF over here, a CS right there. Let's call that middle point VM. I'm going to have a VM right here. Then I'm going to have my GM from the transistor. Again, I'm going to assume the output resistance is infinity. So the only thing that's left over here at the output is the load capacitance. Okay? So I've drawn my small signal model, and now, obviously, I'm going to add in my noise source, in this case, from the GM of the transistor. Okay, so procedurally, obviously, now I could go and just write some KZL and KVL equations and do some integrals and figure everything out. I claim, actually, this is going to turn out to be a really easy problem if we just sort of look at things the right way. Okay? So to do that, I want to ask the following question. If I look at this network here at DC, what's going to be the resistance that I see looking from the standpoint of the noise current over here?
Infinite.
Okay, somebody said infinite. Who thinks it's infinite? Usually more people think it's infinite. Who thinks it's not infinite? Okay, so somebody who says it's not infinite, what is it? Not Will. So what is it?
One over GM.
Ah, okay, you're very close. You're going in the right direction. So Brian said it was 1 over GM. Okay, well, so certainly if I dumped some current into that right there, I'd definitely get a 1 over GM, right? So why do I claim it's not exactly 1 over GM here? What's a little bit different about this particular circuit?
You have a capacitive divider.
Yeah, I've basically got a divider there, right? So if I look at the voltage wiggle right here, I don't exactly get the same voltage wiggle right there. What I actually get, and I'll again go back to my ideal mathematical thing, I basically have some feedback gain ratio there, right? So if I had some wiggle right there, I'm going to get the same wiggle, but just multiplied by f, right? So, by the way, in this particular case, is that feedback gain greater or less than 1? That capital F there. Yeah, it's got to be less than 1, right? It's a divider. Okay, so if I looked at the effective resistance over here, should it be increased or decreased? And I want resistance, by the way, just to be clear.
Increase.
Ah, okay, we got a few. So Will said increased. You guys said decreased or increased?
No, increase.
Increased. Okay, good. It's increased, right? Because basically, the voltage that I'm feeding back into the GM is smaller. So the current it supplies is smaller, which means the resistance is larger. Okay? So now, given everything that we just said, if I had a perfect feedback, we would have said that the resistance was 1 over GM. But now that I have that feedback factor capital F, what is the resistance now? I kind of heard somebody say it. Just speak up.
1 over F times GM.
Yeah, it's 1 over F times GM, right? Because if F is less than 1, that's going to reduce the effective GM, right? So that's my effective resistance. Okay, I claim actually once I've done that, my life is really, really good. Because now this whole thing up at the top over here, I can basically redraw that as something like the following. I'm going to have some effective resistance, right? Which is just that 1 over FGM. And I'm also going to have some effective capacitance. By the way, just to be clear, what is that effective capacitance going to be? And by the way, this is actually pretty easy because there's no magic happening there. So what's the effective capacitance I'm going to get?
CL plus CF in series with CS.
Yeah, so basically I'm going to get CL plus CF in series with CS, which is kind of like the parallel combination when you do resistors, right? So that's CS, CF divided by CS plus CF, okay? Now, just because it's going to make my life a little bit easier, remember that capital F right there is just going to be CF over CS plus CF, right? That's just the capacitive divide ratio, okay? So again, just to make life a little bit easier, I'm going to instead call that CL effective. I'm going to say that it's CL plus CS times F. Okay? And again, that's just to make my life a little bit easier later. Well, once I've done all this, I now just have that R effective in parallel with the CL effective. And then again, my noise current generator. Well, good news is this is now really easy. Right? This is just that standard, first order RC network that we've dealt with a bunch of times. Okay, so everybody finish copying this over. Just going to move to the next page so we have a little bit more room. Okay. So now what it's really going to come down to, and I'll just redraw the circuit right here. It's all just going to come down to figuring out what is the noise I'm going to get. Oops. From that, right? Okay, well, remember the IN squared, that's just 4 KT gamma times GM, right? In general, if I have something like this, then of course what I need to do is figure out the integral of the impedance over frequency, which, if you do it, just turns out to be, just to be clear, Z effective as a function of S there is going to be R effective divided by 1 plus S R effective times CL effective. Okay? Just standard first order thing. So if you actually do that integral, what you're going to get is R effective squared divided by 4 R effective times C effective. Because remember this integral over here, you just take whatever multiplies the s, you do 1 over that times 4, and that's what the integral ends up being for the first order thing. Okay? So of course, that's going to be simplified a little bit further in 1 second, because I have r effective squared at the top, so I just knock this off and knock that off, right? So now I'm in great shape to actually go and calculate the total noise. The total noise is just going to be in squared times that integral, right? And so if I just plug things in, I'm going to get 4 kT gamma gm times R effective over 4 C effective. So now, just as a reminder, or maybe you guys can remind me, what was R effective?
1 over FGM.
Yeah, this was 1 over FGM, right? And again, that C effective, that was just CL plus FCS, okay? If I just basically plug those two things in, obviously I can take the 4 here and cancel that with a 4 there. So I'm going to get KT divided by CL plus FCS. The GM right there is going to cancel with the GM right there. So of course GM falls out of the picture, which kind of is nice because we have this feedback circuit, so everything should be sort of set by the gain, right? So what I'm going to get is gamma over F, right? Does this make sense to everybody, or? Okay, so just like you might have expected, there's some KT over C, and in this case, this C in the bottom is just the total effective capacitance, since we had that capacitive feedback back over here. And then times, that gamma, that's just because there's the active amplifier in there, but this 1 over F, that basically tells you what's the sort of the effective amount of noise amplification you get, okay? And notice actually this F right here, just as a reminder, that F is CF over CS plus CF, is not exactly the same as the gain. Because the gain is again just CS over CF. Right, so just like before, because we were changing the source impedance, we're actually amplifying the noise up by some factor. Okay? So, by the way, you should sort of keep this result handy, or remember how to get there, because this particular topology is going to be showing up, I don't know, order 5 to 10 more times in class, okay, and in homework, and etc. So keep this in mind, because if you know how to do this, you'll be in very good shape to do a whole bunch of stuff moving forward. So, any last questions before we say, noise is all done, and, well, not really, but at least formally just talking only about noise? Okay, so now you guys are all noise experts. You can bang these calculations out in no time at all, right? Okay, cool. So with that, let's actually start talking about some quote-unquote real circuits. Okay, so just to kind of give you a preview or an idea of where we're going to be going, we spent a lot of time talking about the devices and sort of we came up with the design methodology, and then we talked about noise for a while. So now what I'm actually going to start doing is going back and looking at a bunch of components that I'm sure you've all seen before. So things like current sources and amplifiers and biasing. But I'm going to focus on some slightly different aspects. In particular, since we now know about noise, we can figure out how would we actually build these components without actually messing up our noise performance, okay? And so, since they just sort of show up all over the place, because basically anytime you do analog, you need some sort of current source, at least with MOSFETs, I'm just going to start out using those. And we'll see that actually a lot of the stuff that we learn about this will be very directly applicable to things that we're going to care about later on down the road as well, okay? So first, if we start talking about current sources, I just need to sort of remind you of one thing. So when I say that something is a current source, that really means only one thing. It just means the output impedance is high, right? Because any real current source I build won't be perfect. It won't have infinite output impedance. It'll just be something that's high. Now, obviously, when I say high, that means high relative to something else, okay? It means high relative to, let's say, everything else in the circuit, okay? But that's really what makes a current source a current source. Now, even though that's really the sort of fundamental property or the fundamental thing you care about, there's obviously going to be a bunch of other things that are going to come into the picture. In particular, for analog circuits, one thing you spend a lot of time worrying about is, okay, fine, I said I gave you a current source, but how small of a voltage can I actually put across that current source and still really make it look like a current source? In other words, still have a high output impedance. Usually I'll refer to that as something like Vmin. By the way, in analog, why do you usually care about that? Why is that sort of an important quantity? What does that set?
Swing or swing.
Yeah, it usually sets the swing in your amplifier, right? As if you basically compress that current source or it comes out of saturation or whatever, then you don't get the voltage gain you want anymore and you don't get the swing you expected. And by the way, swing is important because the more swing you have, the larger noise voltage you can have, and oftentimes actually you can end up with lower power for the same SNR, okay? So we're going to see swing is a big deal. Now, obviously on the other side of that is how much noise is that current source going to generate, right? Because obviously if that's generating tons of noise and it's just swamping out my signal, that's bad news. The other thing that obviously you're going to care a lot about is just when I say I gave you, let's say, a 1 milliamp current, is it really 1 milliamp? Or is it 2, 3, half, 0.8, right? Basically, how accurate are you actually going to be able to set that? Okay, so we're going to do sort of a brief review of, I think, techniques that you should have seen before. So obviously things like cascoding, or gain boosting, or active cascode. But before we do that, I just wanted to sort of start out and make sure we're all on the same page on a couple of things. So the first thing I want to do is just sort of draw basically the stupidest current source I can think of, and then make sure that you guys all see why it's actually stupid. Okay? So if I wanted a current source and I wasn't a Berkeley student or I didn't take any classes from Berkeley or whatever, then I might do something like this. I might just say, okay, fine, I have the supply voltage. Why don't I just do a resistive divider off that supply, tie it to the gate of that MOSFET, and then have that thing be in saturation, and now I've got a current source, right? Okay, so what's wrong with that? Why did I claim that this is a really stupid way of doing things? There's obviously a long list of problems here, so just start throwing them out.
You have a power area trade-off with the resistors.
Okay, that's true. That's actually not the worst thing, but yes. So I'm going to spend some power on those resistors. I agree with that. Maybe I can make those resistors huge, but yeah, I agree. That's annoying. Anything else that I think is maybe much worse?
Relying on one transistor is going to get you really horrible matching.
Ah, okay. Now, by the way, you said it relying on one transistor gives you horrible matching. It's only one transistor, so matching doesn't exactly mean something. But what are you really saying when you mean matching?
It doesn't track the VT with...
Oh, okay. So now everybody said a bunch of things, right? So the big problem here is variation, right? In other words, if I just set some voltage there, who knows what current that's going to get me? Right? Because let's even pretend for a second that I magically give you a great voltage that's always, let's say, 1 volt, right? So even if I did that, and I magically, set this ratio, let's say I put this at 400 millivolts, great, I have a precise 400 millivolt voltage. I still claim I have absolutely no idea what the current is. So what are, somebody mentioned it already, but, what are like the 2 or 3 dominant mechanisms that would mess up the actual current you get, even if you set that voltage precisely?
Threshold.
Say that again?
Threshold voltage.
Yeah, the threshold voltage, right? Because who knows what the threshold voltage is? Today, maybe they ran the fab with a little bit more doping. Tomorrow, a little bit less. I have no idea what that thing is. So obviously, if the threshold voltage changes, I'm going to get all kinds of different currents at the output. What else is kind of bad about this?
It's
What
not
else
sup-
could change that
It's
you
not
wouldn't
supply
like?
independent or temperature independent.
Okay, yeah. So obviously, if the supply voltage changes, I'm going to get some totally different current, right? In fact, even if the temperature changes, I'm again going to get some totally different current for multiple reasons. One, the mobility is going to change. Two, the threshold is going to change, right? So bottom line, this is, even though I could claim it has high output impedance, this is a really bad current source simply because I really have no idea what current I'm actually going to get. And it's just sensitive to all kinds of stuff that I probably don't want it to be sensitive to. Okay, well, so obviously there's a better way of doing things, which I'm sure you have all seen before, which is basically if I really want to somehow create a current source, I should basically copy that from some other current. Okay? Now, there's a bunch of ways we can create currents that are fairly precise. So, we'll talk about that a little bit later when we get to biasing, but one example is to take like a band gap reference and run that through some controlled resistor. But bottom line, don't worry about that. Let's assume that I really do just give you a current. Okay? So obviously, if I gave you some current and, you trusted that current, then now if I wanted to create a current source, I obviously just build some sort of current mirror. Okay? And again, this is nice because now, as long as the two devices are matched to each other, I don't have to worry about threshold voltage. I don't have to worry about things like temperature or, the processing being a little bit off, right? Basically, as long as I can get the two devices to match each other, which I can do pretty well, I'm basically just going to copy that current. Okay? Now, I'm sort of, as I mentioned, that really somebody has to create that current over there. But actually, a lot of times, even if you're out in industry, if you build some chip, you're just going to say, okay, fine. I'm going to assume that somebody's going to give me one bias current reference into my chip. Okay? And so especially if you're here in academia, that's kind of a nice, easy thing to do. You can just go and buy like external equipment or whatever it is. Or in fact, you can even kind of fake it by just putting a big resistor and a variable voltage. Right? But basically, once you have that nice bias current, now you're just going to want to take that thing and use it kind of all over your chip to bias all of your different amplifiers, right? So let's say, let me just give you some examples. So let's say this is your chip. You've got some amplifier over there, some amplifier over here, some amplifier over there. And again, I'm going to give you some magic bias current, but obviously I don't want to give you like 30 of those things, or 3 even, because you have to hook up the board and it's just kind of a pain in the butt. So what you're going to do is take that one current, and then basically, let's say that's coming from a pad on the chip. I'm going to want to use that to generate a bunch of different currents on the die. Okay? So now usually the first time people do this, they'll do something like what I'm about to draw, and then we'll see if we really want to do that or not. Okay? So if I take that bias current and I feed it into that diode right there, now I should have a voltage that magically will tell me what the current is supposed to be, right? So how about I just take that wire and then put all of the current mirrors locally at each amplifier where I actually want to use it. Okay, so I'm just going to take that voltage and distribute it to the gate of all those mirrors all over the chip. And, just to give you an idea, this is maybe, 10 millimeters by 10 millimeters. Okay, maybe not your chips here in school, but, maybe when you get out. Actually, by the way, even if it's a millimeter by millimeter, the problem will still be actually kind of similar. Okay, so I can do this. It's probably better than the previous circuit that I had built, but I would actually claim that this is also still kind of bad. So What's bad about doing things this way? Okay, voltage. So you said voltage drop in the wire. So actually, let's be really specific. So which wire voltage drop do you worry about? Or to be more explicit, remember voltages are all relative. So when you say voltage drop, what are you measuring relative to what?
Yes.
Okay, so you said VGS. I agree with that. Shiva?
The grounds are not the same. So
Ah, there we go. Okay, so remember, anytime you measure voltages, there always have to be 2 points, right? So as an example, what I called ground right here is not really going to be the same as the ground over there. Because in reality, there's actually some, and maybe let me draw it in a different color just so that it's clear. In reality, there's actually some ground wire going like this, right? It has to span the entire chip. And of course, that ground wire, it's got resistance in it, right? And okay, it's going to go out to a pad or something like that on the 2 sides. But all throughout that chip, I'm going to have other things basically pushing current through that wire, right? All the rest of my active circuits, they're all going to have current flowing through the ground wire. So now, whatever I called being ground right there, which sets the VGS on my diode connected device, even though I take that, wire and run it over to the other side of the chip for the thing that I usually think of as being the bias voltage, unfortunately, the other wire, which is ground, is not actually at the same potential here as it is over there, right? So if I looked at the VGS right there, and let's call that VGS2, ain't going to be the same as the VGS on the left side of the chip, right? Or on the top side, or on the bottom, or basically anywhere. So, bad news, right? Because even though I did all this current mirror stuff, I still have these errors in my output. Well, so how do I fix this? Anybody know? If I really wanted to get lots of different currents, how do I do it? Not Shiva.
Use multiple sources.
Multiple sources. When you say multiple sources, you're going actually in the right direction, but what do you mean?
Multiple different inputs from, like when you're doing layout, you want to use multiple cells, so use multiple inputs.
Almost. So I'm not, so just to be clear, you could be saying, okay, fine, why don't I take another pad with another current over here and connect that locally into a mirror, right? That's kind of what you're saying. I could do that. That would work. If I had a chip with like 100 or 1,000 or even 10,000 amplifiers, I probably don't want 1,000 pads for external bias currents. So I want to find a way to do almost the equivalent of what you're saying. So how would I do that?
Distributed current.
Yeah. And what I really want to do is distribute the currents, right? So basically, in this case, if I had 3 different places I need to go to, what I actually do is locally, at that point right over here where I got the bias current in, I would mirror this thing over to 3 different mirror legs. And then what I would actually do is route those currents out, right? Once I've routed those currents out, at the point where I actually want to use it, and let me just move this wire a little bit so it's easier to see, then I can just mirror it back into another current mirror as if I had something coming from outside the chip, right? So now I'm just creating this quote-unquote external current, but I'm doing it on the die, right? Again, the reason this is good now is because current's current, right? If there's some number of microamps, there's some number of microamps. So no matter what, the supply drop over there is, or what the difference in VDD at this point versus VDD at that point is, doesn't matter because I'm just going to re-reference myself to that local point, okay? So I think we'll finish this up next time, but just as a kind of final reminder, and then we'll take maybe Dan's question. If you're building a chip, whether it's in academia or in your company, and you need to actually get different bias currents everywhere, don't do that. That's a great way to get fired. So, Dan, you had a question?
You still have some pretty long antennas, right? If you were to try to do this.
So you're just saying, okay, fine, I do this whole trick. At some point, I'm going to have to distribute a voltage somewhere, right? And you're absolutely right. But the point there is, if I make that wire short enough, I know very, very well what the voltage drop across the ground should end up being. And in fact, if you look at some of the, the really careful analog designs, there's even ways you can route that ground wire to make sure that you know exactly what the IR drop will be, or to make sure that basically it doesn't cause any error inside of a small local unit. The problem is when you go over the whole chip and you don't know what the whole chip is doing, then you can really get some big errors. A, just because there's a bunch of stuff on the chip that you can't control, but B, that resistance gets really big, right? So if I keep it, let's say, over 100 microns or 20 microns or something like that, I can make sure that resistance is small enough that even if I have a lot of current flowing through there, I don't get a lot of drop across the wire. That's a great question. Okay, great. So I'll see you guys next week.